morning, Mr. Bates. Lovely morning, isn't it?
Morning. You got that new system going yet?
Yes, sir. That is, what I mean to say is I think so.
Oh, come to the point and don't waste words. We have to have efficiency these days.
Yes, sir. The files are nearly all fixed up.
Remember what I said about having things you need right at hand?
Oh, yes, sir. I've been seeing to that.
Where are the Madison Steel Company papers?
Your right hand top drawer.
Don't stand there. Sit down. Take a letter to... Oh, what's this? Did you put this in my desk?
Yes, sir. That's my piece of pie. Here, let me wipe it off your cuff.
Have you gone mad?
Oh.
Your pie and
It's
my...
part of the new system. You wanted things efficient, and you always dictate around 10:30, and I always get so hungry. And you said we should always have everything we need near at hand, so I put my pie in the drawer right next to where I said.
Well, since time-saving of one kind or another seems to be the order of the day, I might as well fall in line. This, ladies and gentlemen, is Excursions in Science. The topic up for consideration is some elementary ideas of physics. And this is our science reporter, Emerson Markham.
Thank you, Bob Stone, and how do you do, everyone? You know what the ancient Greeks said, moderation in all things. Well, it rather looks as though it's up to me to set things at a more moderate pace here. After all, you can't whiz through experiments at breakneck speed and get much out of them.
From which I gather we're going to devote this excursion in science to some more of Dr. Francis J. Norton's Simple Scientific Experiments for the Home, which will give us some elementary ideas of physics.
A good deduction, Sherlock Stone. Physics can be conveniently divided into mechanics, sound, heat, light, and electricity, including magnetism. The basis of all come back to the observations we make by our senses.
Now, what sense is wound up in our appreciation of mechanics, Emerson? Riddle me that.
Well, in mechanics, Bob, some of the basic concepts center in our muscular sense, the feeling of pushing, pulling, or lifting a weight. In the other branches, our other senses take part in the elementary ideas, ears in the study of sound, eyes in light, or a sense of touch and skin sensation in heat, and various combinations of our sensations in branches of electricity. We cannot directly feel, see, hear, taste, or touch magnetism as such, but we can always observe some secondary effect of it.
Well, I haven't been misled, have I? I mean, we are going to consider some experiments with things physical.
Yes, indeed we are, Bob. In the branch of physics called mechanics, there are some elementary sensations of which we are continually conscious, and which form the basis of great developments in the elementary ideas.
That's so? Such as what?
Well, whenever you weigh yourself, you measure the downward force which you exert on the scales. When you pick up a weight, you feel a muscular force which you exert on a weight, and you know that for a heavier weight you must exert more force. You can get a similar comparison of forces by pushing a light body, such as a small cart, or a heavy lawn roller, in order to set them into motion.
Well, I'd rather just contemplate pushing a lawn roller around right now, please.
Very well. Well, here's something else to contemplate. The amount of material in any body is proportional to the weight. Weight is due to the attraction of the earth for the body we are trying to lift, and to an equal and opposite action of the body on the earth. But now consider in our imagination what happens when a certain block of iron of a given weight is in another world or on the moon.
Well, that would take some imagining, I'd say. Why should we go to such lengths?
I was about to point out that the attraction of the smaller moon on the block of iron is less than is the attraction of the earth when the block was weighed on earth. Therefore, a pair of scales on the moon would show a lower weight for this block on the moon. But the actual amount of material has not changed, merely the weight. We give the name mass to this amount of material, unchanged, by taking it to the moon.
Well, how do mass and weight stack up against each other here on Earth, Emerson?
They're proportional, and often used to represent each other, but they are not the same thing.
Oh, no?
No. A given mass is unchanged on taking it to the moon, but the weight is greatly changed. Even on Earth, weight is very slightly different at different places, and measurement of this slight difference is used to explore the Earth for differences in the attraction of gravity.
Let's consider this gravity business for a little.
All right. There are a few interesting things I might bring up about it. First, the force of gravity may be opposed by other forces.
How come, Emerson? I always thought the force of gravity was pretty great.
Well, Bob, here are some experiments you might try to prove my statement. If you hold a pail of water upside down above your head, gravity will pull the water down and give you a good wetting. But if you swing the pail of water and keep it swinging in a circle, you'll find that as long as the pail is in motion, the water will not spill out when it is over your head. This is a good experiment to try. but be sure to keep the pail moving in a uniform circular motion.
And try it out in a vacant lot?
Yes.
Don't you have any other experiments with the possibility of less dampening effects?
Well, when you whirl a stone around you as you whirl the pail, the stone exerts a pull on the string which is called centrifugal force. That is, directed away from the center. At the same time, the string exerts a pull on the stone. You can feel it with your hand. This equal and opposite force is called centripetal force, directed toward the center. Well, now, we've talked about force and mass and weight and have considered the forces of gravitation and of rotation called centrifugal force. Another property of matter related to mass is called inertia.
Ah, this sounds more in my line.
Well, inertia might be called the laziness of matter. It's the tendency of matter to resist a change in the state of motion or of rest. If an object is at rest, it tends to stay at rest. If it is in motion, it tends to stay in motion. All this was stated by that great philosopher, Newton. A body at rest or in motion will remain at rest or in motion unless some external force is applied to it. The statement is called Newton's first law of motion.
Can we try some experiments with this inertia business, or do we just have to let things rest?
Well, there are many experiments you can do to show a body has inertia, Bob. For instance, you can put a small piece of cardboard over the neck of a milk bottle and rest a coin or a marble on it. Give a quick snap to the card with your finger. The card will sail away, but the marble will stay and drop into the bottle. Or you can set a book on end on a sheet of paper. Then jerk the paper away very quickly, and the book will remain upright. You can try this with various small, upright articles. The paper can be given a still faster motion in this way. Allow some of the paper to stick out over the edge of the table. Wet your fingers and strike a sharp blow at the paper. This can give a very fast motion to the paper, and you can thus remove it from beneath various balanced articles.
Reminds me of that trick I've seen done, where the fellow jerks a tablecloth from under a table full of dishes.
Well, I don't think we should recommend that our friends try that one, Bob. But there's a neat experiment illustrating angular momentum.
Before we consider it, please explain this angular momentum.
Well, just as bodies moving in a straight line have momentum, made up of mass times velocity, so bodies in rotation, whirling about, have an angular momentum made up of mass, velocity, and radius of the circle on which the bodies are whirling.
And no doubt an experiment would clear up just how this works?
Probably. This experiment can be done very simply. It gives you a feeling of angular momentum and teaches you something about it. Find a floor space that is smooth, such as polished wood or linoleum. Grasp a heavy book in each hand, extend each outward from your side at arm's length, and whirl around on one foot.
Oh, dear.
You are now a rotating object with weights at the ends of your arms, whirling in a circle. As you are turning around rather rapidly on one foot, quickly bring the books close into your body. You'll find that your rate of rotation is speeded up considerably just by bringing the weights in closer to you.
Well, why does that happen, Emerson?
Well, the reason is that in a rotating system, angular momentum, made up, as I said before, of mass times velocity times radius, tends to stay constant or to be conserved. So when you suddenly change the radius by bringing the books close to you, the velocity of your whirling automatically picks up to make up for the loss in radius, and thus to keep all of your angular momentum as it was. You can do this very well on skates as you whirl around. Throwing your arms out to slow your whirl and bringing them close to your body will make you whirl faster, of course.
Well, thank you, Emerson, but I don't skate. Ladies and gentlemen, we hope you'll try some of these experiments. It'll make familiar to you as real meanings such words as force, mass, weight, inertia, and momentum. After all, as we pointed out during many excursions in science in the past, the whole progress of science depends on the precise and exact meanings of words, as indicating certain experimental results. And the more we understand and appreciate the real meanings, the more all science will open up before us. Now, probably the best way to start investigating will be for you to obtain a printed copy of the experiments we've mentioned. Dr. Francis J. Norton of the General Electric Research Laboratory, who prepared those we've talked about, has given us permission to offer a paper which contains all those which we've talked about plus several others. All you have to do to get your copy of this paper is address your request to Excursions in Science, in care of the station to which you are now listening, asking for Simple Scientific Experiments for the Home, number 148, entitled Some Elementary Ideas of Physics. That's Some Elementary Ideas of Physics, Simple Scientific Experiments for the Home, number 148. And to our regular listeners, it will come as no surprise that we've come to question and answer time. But for the benefit of those who may not be so well acquainted with our usual order of business, it might be a good idea to say that the questions you'll be hearing have been submitted by listeners, laymen with a scientific curiosity in the world about them. The answers are as scientifically sound as possible since they are based on information supplied by staff members of the General Electric Research Laboratory or other equally reliable sources. Well, Emerson, let's get busy with this inquiry from the top of the pile. It's from a listener who is interested in astrology. He'd like us to explain about Aquarius, for it seems that he was born under that sign.
I'm afraid that doesn't belong in this program, Bob. Astrology is not a science. It has no scientific basis nor scientific standing.
It's really a superstition, isn't it, Emerson?
Exactly, Bob. Though surprisingly enough, a great many people believe in it. Similarly, there are many people who believe in divining rods, in the harmful power of the number 13, and numberless other superstitions.
Don't astrologers believe that the heavenly bodies control our destinies, Emerson?
That's right. Long ago, there was some reason why they did. It was perfectly reasonable to suppose that the stars were put in the heavens for our benefit. For the earth then seemed to be the principal part of creation, and to man the most important thing on it.
I suppose those were the days of mythology, when people believed that the planets and heavenly bodies were deities like Jupiter and Apollo, Venus and Mars.
Yes, and they were believed to be not far away, guarding over mankind. So at one time it may have been perfectly reasonable to suppose that when the stars and the planets were together, their influence might combine in some peculiar way.
But now we know the stars are way beyond the planets, don't we?
Yes, we do. Trillions of times as far. But anyhow, your astrology doesn't bother about where the stars are now, only where they were a few thousand years ago.
Is there a change in their position?
Indeed there is. It's principally a motion called precession due to a slow wobbling of the Earth's axis, which takes 25,800 years to complete. As a result, once in this period of time, the constellations slip all the way around the zodiac, which is the path through which the sun, moon, and planets seem to move.
Then when a planet is in Aquarius, according to the astrologer, it's really someplace else.
That's right, Bob. The astrologers go by the signs of the zodiac, which remain fixed, where the constellations were thousands of years ago, while the constellations meanwhile have moved elsewhere. When a planet is in the sign of Aquarius, the water carrier, it's really in the next-door constellation of Capricornus, the sea goat. Surely if there were any of the interrelations between the stars and planets which the astrologer talks about, they would be with the stars as they are, not with where they were at some arbitrary date in the past. But enough of astrology. Let's get on with the real science.
At your service. Now, how about this one? It's from a young man who'd like to know if the layer of air above the atmosphere is called the stratosphere.
The stratosphere is the upper portion of the atmosphere at about 10 to 20 kilometers, or 6 to 12 miles above sea level. It's that portion of the atmosphere beyond the highest clouds. An interesting fact about this region is that the temperature changes but little with altitude. Then, too, clouds of water never form in it, and there's practically no convection.
Isn't this the region which is also called the isothermal region?
Yes, that's right, Bob.
And it never storms, that region?
No. No clouds nor any sort of precipitation. Rain, snow, sleet, or hail, nor any kind of storm, even for a moment, disturb the serenity or overcome the stability of this region.
Now, here's an interesting one from a young lady who would like to know if there's a place in the United States where people walk or stand at angles when they think they're standing straight.
No, I think not. What our listener is referring to, I imagine, is an optical illusion. There are several places in New York State where certain phenomenon has been observed by tourists as they have passed through.
A phenomenon, you say?
Oh, that's about what it is, Bob. One derives the impression when driving along certain roadways that the road is going uphill, when actually it is going downhill.
Then what one actually experiences is an optical illusion then, Emerson?
That's absolutely right, Bob. This is apparently what our friend speaks of when she asks if there are places where one stands or one walks at angles.
Well, the man in the control room probably won't care what angles we assume so long as we start walking towards the door. And right now. For it's time once again for me to say thank you, Emerson Markham, and goodbye, everyone, until our next Excursion in Science.